Hello everyone, I'm Joshua and now I'm going to perform how to design a synchronous counter that counts on the sequence of my student ID, which is 0107334. For my design, I'm going to use T flip-flop, and I'll also show how to upgrade my counter so that it also counts the reverse of the sequence of my student ID. And I'll also show how to design the counter using JK flip-flop. There are usually 5 steps to design a counter. The first step is to decide the number of flip-flop needed. Then we need to draw the excitation table. The third step is to draw the state diagram and circuit excitation table. After we have the circuit excitation table, we can apply the K-map to get the Boolean equation for the logic diagram. Lastly, we draw the logic diagram according to the K-map we get. To decide the number of flip-flop, we should know that the number of flip-flop is the same with the number of bits of the biggest number we need to count. And the biggest number in my ID is 7, which is 111, and it is a 3 bits binary number. So by right, my counter should have at least 3 flip-flop. But to count the repeated numbers, we need 1 more flip-flop. So there's a total of 4 flip-flops needed in my counter. The reason we need to add 1 more flip-flop is we need to replace the repeated numbers with another number that have the same first 3 bits but different most significant bits. For example, 0, which is 0000 in binary number, I need to replace it with 1000, and this 3, 0011, another 3, I need to replace it with 1011. And for the excitation table are a table that shows the next output or step when different inputs are entered with different initial conditions. And to draw the excitation table, we need to know how T flip-flop function first. And this is a T flip-flop. When T is equals to 0, the next stage Q, it doesn't change. But when T is equals to 1, the next stage, which is Q, will toggle. So this is the excitation table. If we want to change the present state 0 to 0, this means that the next state doesn't change, the T will be 0. And we want to change from 0 to 1, the input T will be 1. And we want to change from 1 to 0, T will be 1. And 1 to 1, the T will be 0. Then this is the state diagram. State diagram is the diagram that shows the sequence of the output or state of the circuit. In simple words, it is a cycle that shows the sequence of how the counters will count. So in our counters, we will count from 0000 to 0001 to 1000, then 0111, 0011, 1011, 0100, and then back to 0000. For the circuit excitation table, usually a circuit excitation table will have 3 parts. The first part is the present state of the output, and for this part, we just list down the numbers from 0000 to 1 to 2 and then to 11, which is 1011. Then for the next step, we need to look at the sequence of the numbers we need to count. So for the next step, we see that we need to count from 0000 to 0001. So the present state 0000, the next state is 0001. And from 0001, we need to change it to 1000. So the present state 0001, the next step will be 1000. And we do similarly with other numbers. And lastly, we need to determine the input for the flip-flop. To determine the inputs for the flip-flop, we need to remember that when the input T is 0, the next step will not be changed. But if the input for T is 1, the next step will be changed. So for example, Q3, the present state is 0, then the next stage is still 0. The input for flip-flop T3 is 0. And for Q0, the present state is 0 and the next state is 1. The input for T0 is 1. And this is how we determine the inputs for T flip-flop. And for the rest of the numbers that we are not using, I just put don't care for the inputs. Next, we just apply the K-maps. We need to do K-map for every input of the flip-flop, which is T3, T2, T1 and also T0. And this Q3, Q2, Q1, Q0 is the output, and we just list down the output. Then we put in the inputs according to the circuit excitation table we have done just now. So after we have drawn the K-map, for example for T3, then we need to group the ones in the K-map. We need to group them as largest group we can, and we need to group all the ones. So for this group, only Q3 doesn't change, so this group we have Q3. And for the second group, Q2 and Q0 doesn't change, but Q2 is on 0. So we need to put a Q2 bar. So the Boolean equation for T3 is Q3 plus Q2 bar Q0. And this is how we apply the K-map. And after we apply the K-map, we can draw the logic diagram according to the Boolean equation we have done just now. This is the logic diagram of the counter that we draw according to the Boolean equation just now. And you can see that we have used 4 T flip-flop and 3 OR gates and 2 AND gates. Then I connect the output to a 7-segment decoder and then connect to a 7-segment display. And when I push the button, it changed from 0 to 1. Then 0, 7, 3, 3, 4. And then back to 0, 1, 0, 7, 3, 3, 4. And now I'm going to show how I upgrade the design so that it also counts the reverse of my student ID. The number of flip-flop used is the same with the previous circuit, which is 4 flip-flop used. But we need an extra input M, and when M is equals to 0, the counter will count in normal sequence, and when M is equals to 1, the counter will count the reverse sequence. And the excitation table is the same as the same flip-flop is used. Then this is the state diagram. We have this blue arrow which represents M equals to 0 and it will count in a normal sequence, and this red arrow which represents M equals to 1 and it will count in a reverse sequence. Next, we need the excitation table, and this excitation table will have a new input M, and it is the same when M is equals to 0, but there's a bit different when M is equals to 1. And this is the flip-flop inputs. Then we also need to apply K-map to all the inputs, but for a K-map which has 5 inputs, we need to divide it into 2 parts, which is M equals to 0 and M equals to 1. And we also group the 1 accordingly, and we found that for this 2 K-map, it has the same common group, which is Q3. This means that this output Q3 does not depend on M, so we just write down Q3. And for this group Q1, it is at the side where M equals to 1, so we write Q1M. And this group Q2 bar Q0, it is on the side where M is equals to 0, so it is Q2 bar Q0 and M bar. And we get the Boolean equation for T3, which is T3 equals to Q3 plus Q1M plus Q2 bar Q0 M bar. And we do the same for the rest of the inputs, which is T2, T1, and also T0. So we also got the Boolean equation for T2, T1, and also T0. Then we just draw the logic circuit of this T flip-flop that counts the inverse of my student ID according to the Boolean equation we have get just now. And this is the logic diagram, which is quite complicated, and sorry for the messy wiring. And we can see that when M is equals to 0, then I push the button, it will change from 0, 1, 0, 7, 3, 3, 4, which means that it counts in a normal sequence. Then if I change M equals to 1, then it will count in the inverse direction, which is 4, 3, 3, 7, 0, 1, 0, and then back to 4, 3, 3, 7, 0, 1, 0. Lastly, I'm going to design the counter with JK flip-flop. The number of flip-flop used is still the same, which is 4 flip-flop. And then the excitation table is different with T flip-flop. And we see that if we want to change from 0 to the next step 0, the J must be 0, but for K, it can be 0 and also it can be 1. So we just put a don't K here. And for the next row, if we want to change from 0 to the next step 1, the J must be 1 and K is also don't care. And if you want to change from 1 to 0, J can be 0 and also can be 1, but K must be 1. So J is don't care and K is 1. And we're changing from 1 to 1, J is don't care and K is 0. And the state table is the same as the state diagram for the counter using T flip-flop. Next is the circuit excitation table. The circuit excitation table is similar. Just the output we change to J3, K3, J2, K2, J1, K1, J0, K0. And to determine the inputs for the flip-flops, we see that from when 0 change to 0, from the excitation table, the J and K should be 0 and don't care. So we just write down 0 and don't care for J3 and K3. And we do similarly for the rest of the inputs, and we can get the complete circuit excitation table. And then we also do the K-map for every input. And this is the K-map for J3, K3, J2, K2. And we can get the Boolean equation J3 equals to Q2 bar Q0, K3 equals to 1, J2 equals to Q3, K2 equals to 1. And for J1, J1 equals to Q3, K1 equals to Q3, J0 equals to Q2 bar, and K0 equals to Q1 bar plus Q3. And this is the logic diagram we draw according to the Boolean equation. And also we connect the outputs to the 7 segment decoder and then to the 7 segment display. And the output is the same as the T flip-flop counter. When I push the button, it changes from 0 to 1, 0, 7, 3, 3, 4, then back to 0, 1, 0, 7, 3, 3, 4. It is similar with the counter we do using T flip-flop. And I think this is all from me. Thank you for your watching.